we'll start from current slide. And I guess here we go. All right. I asked before, but not everybody was in here. Any question on anything we've done so far? Okay. We're in Chapter 1 still, Section 1.2, on page 16, the first example, two first-order IVPs. What do IVPs stand for? Initial value problems. Perfect. Okay. Now, back in 1.1, we did a problem 45. That was probably homework exercise. You're asked to deduce that y is equal to CE to the x, okay, is a one-parameter family of solutions of the simple first-order differential equation y prime equal y, okay? I don't know if you did it or not, but it's pretty simple to do. How would you show that is the case? Take a derivative. Good choice, okay? Y prime would be? Say that again. CE to the x. That's your variable, okay? That's it. I love exponential functions, don't you? Easy to integrate, easy to differentiate. So therefore, obviously, these two are equal to each other. Y prime is equal to y. Pretty easy to show, right? Now, it says all the solutions in this family are defined on the interval from negative infinity to positive infinity. Every value x that will work for, okay? If we impose an initial condition, say y, how many initial conditions do we need for this problem? One, because it's a first order differential equation. So we only need one. The other answer to that, there's only one arbitrary constant, so we only need one. So here's our initial condition, y, and it doesn't have to be 0, but it makes sense if it's 0, is equal to 3. Y at 0 is equal to 3. Okay? Now, what would you do with that? Okay, plug in 0 for x and 3 for y, and that should allow you to evaluate c. So y is 3 is equal to c e to the 0. And what is e to the 0? 1, okay? So that's just 1, so c is equal to 3. All right? Okay. Now to be complete about it, you now go back and plug that in. Y is equal to 3 e to the x. And sure enough, there it is. Okay? That's the solution for that differential equation with this initial value. Okay? Now, the graph, let's wait a minute and do the next part. B. Now, if we demand that the solution curve pass through the point 1, negative 2, rather than 0, 3, because saying y is equal to 0, 3, that's saying it passes through x equals 0, y is equal to 3, okay? But now we're going to demand that it pass through, okay, so want a different color here? What color you want? Green. Green, green, it's green, they say, on the other far side of the hill. Okay. We want it to pass through the point 1, negative 2. Okay? So, what would we do? How would we accomplish that? Okay, plug in 1 for what? X, okay? And negative 2 for y, so it would be negative 2 is equal to c e to the first. Okay? So what would c be then? Negative 2 divided by e. Divide both sides by e. Remember, e is just a number. It's also a function sometimes, but it's just a number. 2.71, blah, 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 blah. Okay, so c is equal to negative 2 over e. Okay? Well, that solution then, you have to plug it back in. Y is equal to negative 2 over e to the x. Okay? There is your solution for that one. Okay? Now, that is a rather strange looking way to express it, because this is e to the 1, right? That is a number. So you could say this is y is equal to negative 2 e to the x minus 1. Okay, right? Because this is the same as e to the x over e to the first. That would be e to the 1 minus x minus 1. So that's really the neater way to express that problem. Okay. Now, going way back to pre-calculus, what this one did was a vertical stretch, because you're multiplying the base function, the primary parent function, e to the x, by 3, and that gave you this stretch. Here is your basic y is equal to e to the x. This is y is equal to 3e to the x. You now stretched it up to 3. On this one, what you've done is moved the x one place to the left and stretched it vertically. You've reflected across the x-axis and stretched it vertically. So now it's going down this way, that way, and stretched vertically by 2. So there is 1, 2 on that graph. But you see, anytime anytime the function is positive, you're going up this way. Negative is, of course, going down this way. Here's the one where it's 0, 3. Here's the one where it's 1, negative 2. And if you let your imagination run, any ordered pairs you want to pick that will satisfy the function, of course, it has to do that. You couldn't say, let's see, could you? Yeah, I guess you could. 1, 3. You could just pick any point in the coordinate plane, anywhere, find this function, c e to the x, find the c that makes it go through that point. Okay. Any questions on that? All right. Then, let's do example 2. I think I'll go and erase all this. Now, back on problem 6, which you probably didn't, of exercise 2.2, you haven't done this yet, this is in the future. You'll be asked to show that a one-parameter family of solutions, the first-order differential equation, y prime, let's go back to black. Okay. Y prime plus 2xy squared I've lost it. There it is equal to 0. Okay. Is, and this will be a solution, or at least they'll claim, we'll do this later, y is equal to 1 over x squared plus c. It seems like a weird way to express it, but it is a simple way to do it. If we impose the initial condition y of 0 is equal to negative 1. I like to put the initial condition with the differential equation, y of 0 is equal to negative 1. Okay? Okay. So, that's what we want to do. Now, before we do that, let me just ask a question. Identify as fully as possible what kind of differential equation that is. And we have 3 ways to classify it. First one's pretty easy. Ordinary, got the easy one. Nonlinear, excellent. The other, of course, is first order. Right? First group. Nonlinear, why is it nonlinear? The y is squared there. You can't have any y or derivative of y with any exponent other than 1. Okay, so that is an exponent of 2. Okay, so let's proceed with this. What we want to do, with that being the solution, we want to impose this initial condition to see what C is. So what would you do? Negative 1 is equal to 1 over C. Okay, means yes in Spanish. What does that give us? Perfect. Multiplied by C and divided by negative 1, or that could be just changing signs. You hear the sound effects too. So what is C? Negative 1. So therefore, what is your specific solution then for this one with that initial condition? Y is equal to 1 over x squared minus 1. Perfect. Okay. Now, is that good everywhere? What is the interval over which that is a accepted solution? Okay, here's Laura. Okay, say that again. Okay, it's not good at 1. I'll buy that. That's all. Why is it not good at 1? 0, exactly. Okay? Or, if you factor this, what do you get? X plus 1 times x minus 1. Neither x plus 1 nor x minus 1 can be 0, so x equal negative 1 also is not allowed. Right? So there's two places where it's not allowed. Anything to the left of negative 1, any interval over there will be fine as long as it does not include negative 1. Any interval between negative 1 and 1, that would be perfectly too, as long as it doesn't include either one of those. And any interval from negative 1 or positive 1 to positive infinity, any interval there, that would be good. It can't include an interval that contains either negative 1 or positive 1. Okay, so the other one that we had before, good everywhere. This one you have to restrict. Okay? All right. I think we just hit the first bullet there. I don't know if you have your books yet, but that's considered as a function. The domain of this thing is a set of all real numbers for which y is defined, but y is not defined in x equal plus or minus 1, so therefore you have to exclude those. So considered as a solution of a differential equation, then the interval I in the definition could be taken any interval that does not include one of those, which would be negative infinity to minus 1. Yeah, everything I just said was here. And considered as a solution of the initial value problem, y of 0 equal minus 1, the interval I in the definition could be taken to be any point over which y of x is defined, differentiable, and contains the initial point, x equals 0. Okay? So what does that limit you to? You see, for this to work, you have to have x equals 0. X equal to 0 over here in negative infinity to minus 1 can't be 0 there. It can't be 0 from 1 to positive infinity. So now you're limited not just to any place that's not, but also any place where x can equal 0. So that would be the interval between minus 1 and 1. Or anything that contains that but doesn't ever contain plus or minus 1. So your interval of interest then with that initial condition for the differential equation before you impose the initial condition that, well, actually, all the way along. Because that initial condition, c equal -1, made that the value. So when you did that, when y of 0 is -1, you then restricted the interval of interest to be here. You can't have it there or here, only that portion in the middle. Okay? So, those two examples were both first order differential equations, meaning they had one what? Two answers you can give there. Okay, one, first derivatives, right? Which means the results would be the only one initial value, but what else? Only one arbitrary constant in the solution. If you have a second order, you need two arbitrary constants, and you'll need two conditions. Okay? Now, generally, what are those conditions going to be? If you have a second order differential equation, that means you have y double prime somewhere in it, right? And if you have y double prime somewhere in it, that means what would be your initial conditions? Y at some value, but what would be your second? Y primed at some value. So always look for that. You can't put y double prime. It has to be y and y prime. Okay. So, back in example 9 of section 1.1, which we did do, we saw that, let me get rid of this. Any questions before I delete this? Okay. Oh, and by the way, I keep forgetting this. My holding up the book there and showing you the graph, that doesn't help the people at home at all. I really probably should do the graph. I should have done that. I didn't even think about that. I'm teaching y'all. I keep forgetting I'm also teaching people who aren't here, so I needed to put the graph on there, but too late now. Let's go on. Okay. I'll try to do that next time. Just don't know. Duh. Okay. I like to put the differential equation first. Here's the differential equation. Y or x double prime plus 16x is equal to 0. Okay? And we saw that x equal C1 cosine 4t plus C2 sine 4t happens to be a solution to that. Is a two-parameter family of solutions for that differential equation. It says find a solution of the initial value problem. Starts that way, but now we have two values, x of pi halves. Now here is where I kind of don't like initial, okay, is equal to -2, and x prime of pi halves is equal to 1. And it's just the way I think of things, because usually when I see t being the variable, independent variable, I think initial means when that's equal to 0. That's not always the case. It means some fixed value and then a derivative. And I don't think it has to be the same fixed value. Not in every case. Some cases it might need to be, but not necessarily in every case. Now here's one thing it can't be. It can't be x of pi halves and x at 3 halves pi. That's two conditions, but those are not the same values, and those are called boundary values. And this initial value problem and a boundary value problem are somewhat different. So we won't go there yet. I don't think we're going to hit there, but if we do. All right, so what would you do? You're asked to find a solution for this problem, which has two initial values, or two fixed values. How could you answer that? What is the process by which you would find the answer? Oh, okay, good idea. Let's take a derivative. X prime is equal to, okay, 4. You said C1. What else you say? Okay, let's put the minus there and put sine of what? 4t. Okay, I buy that. Plus 4 C2 cosine 4t. Perfect. Okay. Now we've taken the derivative. Does that give us our answer? Monica? All right, we just get some Jasmine. Okay. Okay, he likes taking derivatives, I can tell. Okay. But how does that help us? Okay. So now we plug in when x, okay, I'm sorry. When t is equal to pi halves, x has to equal -2. So what do we do? -2 is equal to C1 okay, cosine 4, I'll write it down, 4 times pi halves plus C2 sine 4 times pi halves. I didn't leave enough space, did I? Okay. Well, what is 4 times pi halves? Second? 2 pi. Okay, so this is going to be 2 pi, and this is going to be 2 pi. Okay? And what is cosine of 2 pi? 1. Okay, so this will be -2 is equal to C1 times 1 plus C2 times what is sine of 2 pi? 0. Hey, we just got our C1, didn't we? C1 is equal to -2. Okay? Now with the x prime, which I know you're looking forward to, and that's why you had me do it early, you plug in as well. And what is your x prime? 1 is equal to -4c1. And what is sine of 2 pi? 0. Okay, we'll just forget that one. Plus 4c2 times 1. All right, so we have our equation 1 is equal to 4c2. So what in the world is c2? 1/4. Divide both sides by 4. Okay, so write down what your solution is. X is equal to, C1 is -2, so -2 cosine 4t, and then your C2 is 1/4 plus 1/4 sine of 4t. There is your solution to this problem. The solution to the generic form had 2 constants in it. Random parameters, it could be any values that make it work through. The 2 initial conditions let you identify a specific solution that is the solution to that differential equation. Sure, it's in that form, but this one in particular, because it matches our initial conditions. And we have 2 of them. So we have 2 constants. Okay. Now, that's your solution. Now there's another blurb here, and several of you don't have your book, so I'm going to have to probably write this out pretty poorly. But any questions on this before I delete it? Okay. All right. There's discussion on existence and uniqueness. So it says 2 fundamental questions arise in considering an initial value problem. The first, does a solution of the problem exist? Okay? So that's the first question. And the second question, if it exists, is it the only solution? Are there other solutions that might work as well? Okay? And for the first order initial value problem, that number 2 that we did earlier that had the vertical asymptotes and the other, the question is, does the differential equation, and that differential equation, that generically would be dy dx, I say dy dx and write dy dy, I don't know what's wrong with the brain today. Okay. Equal f of xy, some function of x and y, and you saw that was what we had in that example 2. Okay. You could have rearranged it and had that. Does that possess solutions? And for the one we did, we said yes. There may be some that there are no solutions, that you can't possibly get there from here, okay? And then the second part, and this also is a, remember you have the boundary values, the initial values. Do any of these solution curves pass through that point x0, y0? Now, before I was about to say, you remember that one that had exponentials? You could pick any point on the board. This isn't true for all. You can make an exponential function go through that, because every value is there. But that's not true. That wasn't true of example 2, where there were some places you just couldn't go. X could never be -1 or +1, okay? And you couldn't, let me just give you another example here. And again, I should be drawing this on the board, but I'm not. Okay? Any point up here is not going to work because that function never goes up there. Or the boundary values that we chose, that they gave us. Over here, none of them work. Over here, none of them. Up here, all those. You can pick a point anywhere, and that you can make a exponential function go through that point. Not so down here. See, I started to say that up there, but nope, this one will work everywhere. This one will not. For those initial and boundary conditions, no, there is just one. Initial conditions, okay? So do any of the solution curves pass through the point x0, y0, okay? If you had chosen that, if that x0 is either +1 or -1, not going to happen. Okay, uniqueness. When can we be certain that there is precisely one solution curve passing through the point x0, y0? That's a tougher question, okay? In examples 1 and 3, a solution is used rather than the solution of the problem, okay? In their verbiage there. Let me see right up here. Thus, y is equal to 3x to the 3e to the x is a solution. Down here it said, hence, blah, 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 is a solution. But on this one, they said, does, blah, blah, blah. Oh, I don't even complete the sentence there. Well, they weaseled the way out of that. But that one would have said the solution, okay, because there would be only one value that would have 0, -1, okay? Now, why do they bring this up? At this point, it has not been demonstrated that there's a single solution to each of each problem. The next example illustrates an initial value problem with more than one solution, okay? And here we go with example 4. Okay, I think I'll delete this so not mess up the thing. Okay. Here is your differential equation. dy dx is equal to xy to the 1/2. What are some things you could tell me about that differential equation? Classify it 3 ways. Second, nonlinear. He likes that one, okay? Nonlinear because the y is to the 1/2 power. To be a linear differential equation, the y's and all the y primes, however many you got of them, can only be to the first power, not to second power, not to fractional powers, not to negative powers, have to be to the power 1. So otherwise, that would be a ordinary first order differential equation. Nonlinear though. Okay, good deal. Now, here's your initial condition. Y of 0 is equal to 0. Okay? Now, there's your whole problem. They give you, because we haven't done it, can any of you just look at that and come up with a possible solution? That you know will be true. If I threw in the word trivial, would that help you? Any trivial solution that would work? 0, 0. If x equals 0 and y is equal to 0, first, if y is equal to 0, what's the square root of y? 0. And what's the derivative of y? 0, okay? So then you have 0, which is the derivative of y, is equal to 0 for x and 0 for y. Okay? 0 for y, the square root of 0. The square root of 0. So 0, 0 is an obvious, albeit trivial, solution to that differential equation. Well, there are others. Okay? And here is an other. So they say here, y is equal to 0 is a solution for that anywhere, okay? Well, especially with x equals 0, y. Well, actually, y is equal to 0 is a solution for any x, okay? Because if x was 17, y is equal to 0, the root of y is 0, and the square root of y is 0. So that's going to be true everywhere. For every value of x, y is equal to 0 is a solution. And when you do y is equal to 1/16, and we did this one earlier, x to the 4th. That's also a solution. You can go back and verify that. Let's just do it quickly. What are 2 things you're going to have to determine to verify that? Just doing this because this is the kind of thing your first test is going to be doing, is verifying. So just to get you used to doing that, what do you have to do to verify that that is a solution for that? I did the y is equal to 0, or y'all did it. Actually, I asked you the question. Derivative of y is 0, and the square root of y is 0, and 0 is equal to any x times 0. Okay, that verified that y is equal to 0 is a solution to all values of x. What would you need to do to verify that's a solution? 2 things. Take a derivative. That's 1. So what is y prime? Not that hard. 1/4 x cubed, right? Okay. And what's the other thing you got to do? Can y'all see that? Say again? Yeah. Well, Not quite. You also have to do, this is y, there's y prime, but what don't you have? Can you see my little cursor? What is that? Y to the 1/2. Do we know it? Yeah, what is it? Y to the 1/2 is, say again, 1/4 x squared, the square root of y. That's what y to the 1/2 is. Take a square root of it, okay? Now that we have those two pieces of information, let's plug those in. Is indeed 1/4 x cubed. That's what y prime is. Dy, let's write it this way. Dy dx, okay? Maybe I should have written that way, okay? Is that equal to x times the square root of y, which is 1/4 x squared, yeah, sure it is. 1/4 x times x squared is x cubed. Yes, those are equal, okay? So it solves that. Does it also satisfy the initial condition? Certainly this one does. Y is equal to 0 satisfies the initial condition 0 equals 0, 0, because that is good for any value x. It doesn't matter what x is, including x equals 0. Is this also good for this value? Okay? Let's see if it is. Okay? Now, one thing that sort of bothers me a little bit, well, they've already, never mind. Okay? Let's see if that satisfies the equation. When x equals 0, is y also equal to 0? So we plug in here, y is equal to 1/16, 0 to the 4th? Sure! That's going to be 0. So y is equal, so that satisfies the differential equation and the initial condition. But so does it satisfies the differential equation and the initial. Okay, so that has at least two solutions, and they show the graph, and now this time I'll remember to do this. Okay, first y is equal to 0. I'm going to do it like they did in the book and do that in red. There's y is equal, y is equal to 0. If I could draw a straight line, that's on the x-axis, okay? That's what it meant, okay? And the second solution is 1/16 x to the 4th. They did that in blue, so let's do that in blue. It also intersects at 0, 0. Both of those do, so the initial condition is met, and then it'll be, let's do 1, 2, 3, 4, 5, 6, negative 1, 2, 3, 4, 5, okay? When x is equal to 1, y is equal to 1/16, okay? Let's, yuck, get out of there. Okay, 1, 2, 3, 4, 5. We won't need very many. Okay, there's 1/2, 1/4, 1/8, 1/16, right there, okay? Why is it doing that? This thing drives me nuts. I was trying to write on the screen. Let's see if an escape will work. Nope. I'm going to have to shut down PowerPoint and bring it back up. Sorry about this. Sorry. So I've lost it all. Let's go back and do just the graph again. This aggravates me. Okay. All right. The red was that function, that's y is equal to 0. And the blue, Let me go back and put my tick marks in black this time. 1, 2, 1. Okay, so 0, 0, oops, get this in blue. Oops, so. Okay, that blue. Okay, 0, 0, 1, 1/16. There, it's doing it again. Okay, and negative 1, 1/16, and our function here is y is equal to 1/16 x to the 4th. Okay, when x is equal to 2, 2 to the 4th is 16, and 1/16 of that would be 1. So that would be here and here. And when x is equal to 3, what's 3 to the 4th? 81. And someone do 16 into 81 quickly. What is that? Anyone got a calculator? 81 divided by 16. Something over 4 to 5, right? Second? Not on the nose, is it? Wow, okay. Closer than I thought. So that would be 1, 2, 3, 4, 5. So we can just barely fit that on the screen here and here. Okay, somewhere right up in there. So here's what this function looks like. Something like that. So both of those are solutions to the differential equation. Both of them are solutions at 0, 0. Okay. Now, any other initial condition, this will still be a solution to the differential equation, but that's the only one that you'll get that to match with the other. So at that particular point, both are solutions. Here, it's not. This is not a solution for that, or here, or here, or here. Anywhere else, it's only right there. They are solutions to both. Okay? So that one does not have a unique solution for that differential equation at that initial value. Okay? There are 2 or more. So existence, yes. Uniqueness, no. Okay. This is the next statement, sort of, I don't know. Within the safe confines of a formal course in differential equations, one can be fairly confident that most differential equations will have solutions, and that solutions of initial value problems will probably be unique. Not necessarily. Real life, however, is not so idyllic. Therefore, it's desirable to know in advance, try to solve these, whether it's the only solution to the problem. I don't want to read the whole paragraph. I'm just trying to get you the general flow of it. Let me write down the first theorem, though. That should do most of it for us. Okay? And here's that first theorem. Let's go back to black. Okay? Theorem 1.2.1, existence of a unique solution. So this covers existence and uniqueness in one. Let R, anytime you see a capital R like that, think region, and particularly in this case, a rectangular region. Be a rectangular region, okay, in the xy plane, or any variables, okay, defined by, okay, A is less than or equal to X is less than or equal to B, and C is less than or equal to Y is less than or equal to D. That's pretty common kind of way to define a rectangular region. That contains some point goodness gracious, I can't write. I'm trying to write too fast. Some point x0, y0. Okay? Now, guess what? That's going to be the place for your initial condition. Y of 0 is equal to x at some value, 0 or whatever. Okay? Now, what that means, x0 has to be between A and B, and y0 between C and D. So you just move your rectangle till it contains the point in question. That's your initial condition. Okay? In its interior, not on the boundary. X0 can't be A or B, and Y0 can't be C or D. It has to be on the interior. Okay. In its interior. Okay. If f of xy, okay, and, whoa, I said before we aren't really going to deal with partials except where they have to be, and here is one. The partial of f with respect to y are continuous on R. Okay, now why do we need a partial there? Remember, f is a function of both x and y. Okay, so therefore when you take the partial derivative of f, it has to be a partial derivative because it has two independent variables. So we're just saying the partial of f with respect to y, not saying anything about the x. If both the function and the partial with respect to y are continuous on that region R, okay, then there exists some interval sorry I'm having to write all this out, but not everybody has books. Some interval I0, okay, and here's how we'll define that. Sorry, I don't have room to put it there. Let me put it down here. x0 minus h and x0 plus h, okay, where h is some small value but greater than 0, also contain in AB okay, and I don't think we allow it to be on the boundary either, but it has to be in that. See, that's one of the reasons we had to have this being in the interior, the x0, y0, because if that was on the boundary, then you couldn't either add or subtract an h to it and still be on the boundary. If the x0 was A, then it's going to be, this one's going to be outside. If it was B, this one's going to be outside. So you have to have it on the interior, the x0, y0, so you can have some small h, positive h, so that fits. Okay? Sort of a little nitpicky point, but it's true. Okay? And the unique function, okay, let's go back and get the whole sentence here. I've interrupted. Then there exists some interval I, as listed here, contained in AB, and a unique function y of x y as a function of x defined on I0, okay, that is a solution for the initial value problem. Okay. So, a lot of blah, 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 okay? What it gets down to, okay, you have some rectangular region, xy plane, those kind of things, okay? Containing some point x0, y0 in the interior. If there is some function, f of xy, and the partial of alpha with respect to y that are continuous on R, then there exists some interval in that I that's between x0 plus h and minus h containing a and a unique function y of x defined on I0 that is a solution. And did I say unique? I think it already said that. It said it was unique earlier of that initial value problem. And that initial value problem is the one that was listed as equation 2 way back at the beginning. This is helpful here. dy dx is equal to f of x, y. Okay? With initial condition y0 is equal to, y, yuck. Let me just do it the same way the book did it. Okay. Alpha of x0 is equal to y0. No, they said y of x0 is equal to y0. Okay. That was our initial problem. So that sort of filled in some of the blanks here. That's your alpha of xy here. That was your first derivative of this. Okay? Now, what is required for it to be true? That this thing has to be continuous, and the partial of alpha with respect to y also has to be continuous. If both of those are met, then you have a unique solution. Now, don't know if you remember your partials well enough to know what it means for that to be continuous. That means, of course, you know that the partial with respect to y has to be a continuous function in that interval R. Okay? So you have to restrict the R to make sure. For instance, if that function was one of those that, say, had a 1 over x minus 1, x squared minus 1, you can't have either x plus 1 or minus 1 in that. So you have to have that partial being continuous on that same interval R. Yeah, in that rectangular region. Okay. Now, that's fairly I don't want to say vague, but it's esoteric. You know, it's just somewhere out there. I think you'll see when you work on some of these, and I think that's going to be what example 5 is. So I don't have room to keep this on there, so I'll go ahead and erase. Okay? Everybody got it? Let's do example 5. Let's go back to example 4. Okay? Here's your function. dy dx is equal to xy to the 1/2. Okay, we beat that function to death, haven't we? Now, and we saw it possesses at least 2 solutions whose graph pass through 0, 0. Okay? Let's see what the problem is. Okay? Well, here I've issued your alpha of xy. In this case, that's what your differential equation is equal to. So that's equal to xy to the 1/2. Okay? Now, you remember the second condition, the partial of alpha with respect to y. And what is the partial of alpha with respect to y? Remember how to do those? Partial derivatives? Second? X over. Second? 2y to the 1/2. Okay. Read that from the book or did it in your head? Oh, good. Excellent. Okay. All right. Yo, you don't have a book. That's good. Probably what I would have done would be a 1/2 x y to the minus 1/2, and that moves it down here. So yeah, that is the vector. Okay. Now, the question is, the requirement is this has to be continuous, okay, and this has to be continuous. Is this continuous? Or where is it continuous? or is it not continuous? Where can that not be even exist? Second. At y is equal to 0. At y is equal to 0, that doesn't exist. So therefore, the conditions in that theorem aren't met here. Because at 0, 0, because at y is equal to 0, this first partial derivative of f with respect to y is not defined. So therefore, that threw out the value y is equal to 0. Okay? Which is, yeah. So that function could not be, it is not unique there because it fails that test. Does that make sense? Okay. Now, if you have some other interval, say centered at 2, as long as it doesn't include 0, 0, that will work. In other words, any interval that's, say, 1 to 3, 0.5 to 17, 0.01 to 85, any interval that doesn't include 0, then that would be perfectly... Oh, wait, well, I'm sorry. It says centered at 2. I would say just containing 2, but certainly centered at 2. In which that... Oh, they actually give it. Y of 2 is equal to 1. Okay? That will be quite doable. And that will have a unique solution. Because when x is equal to 2, this is unique. This is a continuous function. Okay? All right. And where that is met, I'm sorry, on the wrong one. It has a unique solution. Back in example 1, okay, and if you remember example 1, that was the y is equal to ce to the x, the real simple thing. We said it was true everywhere. So let's do that one. Y is equal to ce to the x. Okay? Now, what's the requirement for uniqueness? That the partial, okay. Okay. You also need the differential equation. dy dx is equal to y. I think that was it, wasn't it? Yeah. Okay. So, what is required is dy, the partial of y, with respect to I'm sorry, the partial, okay. This is f of xy, okay? So the partial of f with respect to y is what? Partial of f with respect to y. There's your f. What is that? F of xy is equal to y. What's the partial of f with respect to y? 1, okay. And that's good everywhere. It's continuous everywhere. So therefore, that function is going to be true. That's why we can say from negative infinity to positive infinity. There's no doubt about that. Okay. So, do we still want to talk more about an interval of unique existence and uniqueness? Some of this gets so bogged down. I don't see anything particularly rewarding about reading that next paragraph, nor the remarks. Now here I mentioned earlier, so I do want to say in the remarks something about boundary conditions. Initial conditions are prescribed at a single point x0. I said before, sometimes you might be able to do more than one, generally at some single point. So y at some value has some value. Y prime at some value, the same value has some different value. Okay, always has to be at the same x value. Okay. We're also interested in solving differential equations which are subject to conditions on y of x or its derivative that are at two different points, x1 and x2, okay, or x0 and x1. Those are called boundary conditions or boundary value problems. So y of 1 is equal to 0 and y of 5 is equal to 0. Here's a sort of a dumb example to this. If you're wanting to talk about the differential equation that governs the vibration of the guitar string. Any of you play guitar? Okay, well, when you press down on the fret, you are fixing this at 0, and then at the end at 0. Okay? So this may be x equal something at 0 and x equals 17 at 0. Whatever you're doing, that is going to define a boundary value. 0 here and 0 there. Okay? The initial condition was it has some fixed value here, and the derivative has a fixed value there. Always at one point, not at 2 points. Okay? Just a dumb example, but there are plenty of others. You might be interested what's going on at the boundaries. Or y at pi halves is 0 and y prime at pi is 1. Those are boundary conditions when they're at different points of x. A differential equation together with blah blah is a boundary value problem. Okay? And then they said we're going to talk about this later. So the mathematical description of many problems in science engineering involve second order initial value problems or 2-point boundary value problems. We will examine some of those in chapters 4 and 5. Hopefully we'll get there. Exercise set 1.2. And by the way, the answers to the odd number problems are on in the back of your book. Now, that's all you got, so I give you odd numbers. Do number 1. Do either 3 or 5 or both. Either 7 or 9 or both. Either 11 or 13 or both. Do 15. Any of the odds 17 to 23. Either 25 or 27 or both. And then any of the odds 29 through 33. You choose. These are on page 19, 20 so far. Any of the odds 35, either 35 or 37, okay, or both. And now we're getting into page 21. And any of the odds 39 to 43. I know those, or I think all those have answers in the back. The discussion problems may not. So take a look at the discussion problems. See if the answer is in the back. If it is, then see if you can work through those. If it's not, I wouldn't, I hate to say it this way, waste your time doing it because you can't check to see if your reasoning is right or not. But check those answers first before you start doing the problems. And you can do any of those odds too. So let's move on to section 1.3. Okay. All right. Now, we can't go into great detail here. I just want to give you a flavor of some types of problems that you're going to potentially run into that you'll need to know differential equations to do. So these are differential equations as mathematical models. I want to give you a few hints when you're dealing with those. A mathematical description of a system or phenomenon is called a mathematical model. Okay? Construction of a mathematical model starts with identifying the variable, or variables, usually more than one, that are responsible for changing the system. We may choose not to incorporate all the variables in the model at first, maybe adding them as we need them, depending on what level of resolution. For instance, now this is a pretty lousy example, but It's reality. My wife is a researcher at UAB. She's an epidemiologist. She studies diseases, or the main diseases she studied has been cytomegalovirus, okay? And that's a disease that if you and I were to catch it, you hardly know you had it. It might feel like a mild cold or a real mild form of flu or something, be over in a couple of days, no negative consequences. However, if a woman contracts it, and again, hardly even notice she had it while she's pregnant, she can pass that to the child. The child may not have any negative result from it, or it could have mild to severe to extraordinarily severe outcome, okay, as a death of the child. Some of the milder ones, they could have no results at all. That's good. But some of the milder ones would be hearing loss. And part of her research has found that a lot of hearing loss in young children that prior to this, then unknown cause, okay? Maybe they had a fever and they lost a hearing or stuff like that. Many of these can be attributed to CMV infection. The trouble is, the child could have picked up CMV after birth, and that couldn't cause hearing loss. It would only be in utero that it would cause hearing loss. So there's you have to test the baby very shortly after they're born to see if they're positive or negative. If they're positive and then later develop hearing loss, that could be the cause for it. If they're negative at birth, but later get hearing loss, you may not know. It wouldn't be CMV. So anyway, she studied this disease. So she had to determine what are the variables that may be important to study. Well, one indicator might be low birth weight, okay? Say gender of the child, no, not at all. Say whether they had prenatal care, possibly. Whether they had a sibling in daycare. Whoa, it goes up big time. So you see, there could be tons of different variables out there. You have to decide which ones have the greatest potential of being relevant, okay? Gender of the child, absolutely not. It doesn't matter, okay? But some of the others may be very important, some be marginally important, okay? So that's what it means by, in that step, you're specifying the level of resolution of the model. You want to hit the big variables first, see how much of the outcome you can predict with those, and then determine, do I need to refine that any further? Then I may take a few more variables that may not be as important, but may be somewhat important. Okay, number two, we make a set of reasonable assumptions or hypotheses of the system we're trying to describe, and those may or may not be valid, and they may mess up your whole study. But we try to do things that make sense, okay? For instance, her major professor was always big on biological plausibility, okay? Is there any reason that these things should be connected? Maybe there is a connection, but can you biologically, it may be there's some other factor that influences both of those, that's a confounder or something like that, that maybe. But this factor has nothing to do with this one because there's no biological connection here. But if you find the true factor, yeah, that would work. So you also want to do that. Let's not get into too much more. There is a little, I don't know if you need all this or not. Get your book or find a book, an e-book or something, and you'll see a little bit more of this. So let's talk about one more thing on the mathematical model. A solution of the model gives a state of the system. When you define the differential equation with the boundary or initial conditions, usually initial conditions, you've just set it fixed, okay? That's the state of the system, okay? So here's just a bunch of possibilities that you could run into. Population dynamics, okay? One of the earliest attempts to model human population growth by means of mathematics was an English clergyman, amazing, and economist, it's really not that amazing, Thomas Malthus. I don't know if you've heard of him before, but it's not too amazing that the clergy would have also been scientists, because quite often the clergy, especially back in the very early times, like Middle Ages or coming into the Renaissance, sometimes the clergy were the only, if not the most, if not the only, educated people in the society. Back in the Dark Ages and the Middle Ages, the clergy were the only one that studied anything. You know, everybody else was just trying to do subsistence living. The clergy were keeping knowledge alive, so he wasn't that early, but he, anyway, let's move on. Basically, the idea behind the Malthusian model is an assumption. Here's his assumption. The rate at which a population of a country grows at a certain time is proportional to the total population of the country. Okay? So let's get that down. When you see the terms rate, that usually means time rate, unless it's specified otherwise. Okay? The rate at which you travel is the speed at which you're traveling. The rate at which you're consuming gasoline has nothing to do with speed. That would be miles per gallon, say. But the rate at which you're traveling, that would be miles per hour. Okay? So usually that is a time derivative. Okay? So let's get that again. The rate at which the population of a country grows, so let's let the population equal P. So the rate at which it's growing, dP dt. You assume it's a time rate. Okay? Now, is proportional to, there's a funny little symbol that looks like that. Kind of looks like an alpha, kind of looks like a fish. I don't know what, it looks like a goldfish to me. If it had a smile on it, it would be. Is proportional to the population itself. Okay, if you have a really, really, really small population, it's not going to grow very fast because you don't have that many pairs in the population to increase. But once you get plenty of pairs out there, then it can take off and go. So here is a differential, well, it's not quite a differential equation, it's a differential proportion. Okay, so how do we change a proportion to an equation? Anyone know? Introduce a constant proportionality. So that would then go to dP dt is equal to kp. I just chose k. Yeah, that's what they chose also. Okay? Where k is that constant proportionality. Now, he's talking about populations of the country. Guess what? This would also be population of bacteria. Okay? It would be population of deer. It would be population of hummingbirds. You know, it could be any kind of population of insects. You know, it could be possibly a population of viruses. Okay, or maybe a population of infected people. The rate at which that grows. So you see, this kind of thing has enormous possibilities for research as a very simple initial condition. Going to be proportional to the population itself. Okay? Populations that grow at a rate described by this are very rare, but it's still used to model the growth of small populations over short intervals of time, like bacteria growing in a petri dish. They still use that. Okay, there's one. Now, of course, to get more things, you could find more variables, more conditions and things like this, and you can act on that. Okay, here's another. Radioactive decay. This is a bit more specific. The nucleus, okay, it goes into protons, neutrons, that kind of stuff. Many of the combinations of protons and neutrons are unstable. That means radioactive. Okay? In other words, they're going to break down after some fixed time. Okay? Such nuclei are said to be, okay, they said that. For example, over time, the highly radioactive radium, which is, okay, this is different, Ra-226. Now that means the radium that has that as a mass, atomic mass, okay, radium-226. it's just too heavy. It's got too many neutrons, basically. It transmutes by radioactive decay into radon, Rn 222. Okay? Now, what did we lose there? We lost a mass of 4. Okay? And anytime you see that in radioactive, think alpha emission. An alpha particle is basically the nucleus of a helium atom is 2 protons, 2 neutrons. And that would account for that, and that's exactly what happens when radium-226 decomposes to an alpha particle and radon. Okay? Now, it lost 2 plus charges. Okay? So that meant it went down 2 steps, and I don't think we have a periodic table here, but if you find radium in the periodic table, down 2 steps is radon over here, 222. Now, so what? Okay? Well, radon is a radioactive gas itself. And that radon, being a gas, that radium is a solid. If it's in the ground, it stays in the ground. Okay? If it's wherever it is, it just stays right there. It's a solid. But radon gas is free to move anywhere it wants to because it's a gas. And guess what? It's also a noble gas. It's a column 8 gas. Helium, helium, argon, xenon, neon, then xenon, stuff, but then radon, way down at the bottom. Anything with that big of atomic mass, if it's a gas, it's a noble gas. It doesn't react with anything. Nothing else with that kind of heavy atomic mass is going to be a gas. That's a gas. So it's free to move. So if your house is built on top of a source of radium, okay, even though it's a very small amount, and that radon gas escapes and comes into your basement or crawl space or whatever, then it could be in it. And guess what radon does? It's also radioactive. So once every about 4 days, about once every 4 days, it's going to also decompose. Okay? Its decomposition, I don't think just involves but whatever it does involve, if you happen to breathe in a lungful and have some radon in that gas that you breathe in, and that happens to be about the time it's going to radioactively decompose, even if it's something as simple as an alpha particle, which I think it does give off, that can cause damage inside your lungs. Alpha particle is not going to hurt you if you have on even a shirt or a piece of paper. It's not going to hurt because it doesn't go far. But if in your lower parts of your lungs and it decomposes, the alpha particle can damage tissue very easily. And if you have enough damaged tissue that your body can't repair the tissue in time, that could lead to an irritation that could lead to lung cancer. And actually, radon gas is, I believe, the second leading cause of lung cancer, only after cigarette. Or cigarette, by far the largest. After that is radon, which is not very. But you don't want that in your houses. So that's why a few years ago, there was a big move on testing homes for radon. Make sure, especially young kids whose lungs are just forming, they aren't breathing lots of radon. But that's just an example. I got off onto it. Sorry about that. And guess what? The To model a phenomenon of radioactive decay, it is assumed that the rate at which a nuclei of a substance decay is proportional to the amount or the number of nuclei. So guess what? Same as before. dA dt, the rate at which they decay, is proportional to the amount that you have, okay, to begin with, okay? And that then would be dA dt, and they just love the constant K equal Ka. So that's exactly the same form here. This is talking about populations of anything. This is talking about radioactive decay, or radioactive activity. If you have a radioactive substance, the rate at which it's decaying is proportional to the amount. So if you have just a little bit of radon in your basement, the odds that it's going to be any problem pretty slim, okay? Because it's not going to happen very frequently. If you have tons of it in there, yeah, you can easily have a pretty serious problem, okay? Okay, literally not tons, you wouldn't have that. Okay. Now, one difference here is this K is usually a positive number because populations grow, radioactive decay declines. That's why they call it decay. Okay? So K can be positive in this case, negative in that case. Two different problems. I mean, very different problems. This is something going like this. This is something going like this. Okay? Radioactive decay. All right. A single differential equation can serve as a mathematical model for many different physical phenomena, okay, as we just saw there. But with different K's can be very different results. Now, if I were to ask you for who is the greatest physicist of all time, I bet you y'all could come up with a list of probably, let's see, what is it, 6 people in here. You probably come up with at least 5 different physicists. Who would be some of the greatest physicists of all time? Name a few. Newton, okay, right off the top, okay. Einstein could be listed, there's several others, okay. Thought probably people would come up with Einstein first, but Newton certainly would be. How about greatest mathematicians of all time? Newton, yeah, he's the one that came up with calculus in the first place, okay? Newton's pretty impressive character, okay? And in addition to everything else, and probably because of everything else, he came up with a lot of other things. For instance, and we still use it, Newton's law of cooling or warming, whichever it happens to be. According to Newton's empirical law of cooling and warming, this makes sense, the rate at which a temperature of a body changes, so guess what that would be? If T is temperature, okay, the rate at which it's changing would be dt dt. Now that's a little bizarre. That's why I put temperature as a capital T, because time is a little t. So that would be the rate at which temperature changes. Okay? Now, the rate at which a temperature of a body, that could be your body, it could be the roast you pulled out of the oven, it could be the ice cube that you pulled out of the freezer. I mean, it could be any body, okay? The rate at which the temperature of a body changes is proportional to, there's that symbol again. Now let's think. The rate at which you pull the roast from the oven. Oven is pretty hot, right? So the rate at which that oven's going to cool, if you bring that roast out into a 70-degree room, it's going to cool fairly quickly. If you bring it out into a 150-degree room, which hopefully you couldn't have, but that's not going to cool as quickly because the room's so hot, right? If you pull it out into a freezer at 0 degrees, it's going to cool even quicker, right? So the rate at which it cools, the temperature changes, is proportional to the difference in temperature between its temperature and the ambient. And that's what Newton's rate of cooling is. It's the proportional to T minus T0, where T0 is the ambient temperature. The temperature you bring, they use Tm. Okay, I'm used to T0. Okay, Tm. Okay, what do they say M stands for here? Maybe nothing. Tm is the temperature of the surrounding medium. That's why they use M, the medium. Okay, the air, the whatever. Okay. think of the ice cube you pull out. If you pull out the ice cube into the kitchen at 70 degrees, it's going to cool and melt at a certain rate. If you take it outside where it's 90 degrees, it's going to melt even faster. If you take it out of the freezer and put it in the refrigerator, it's going to melt much more slowly. So the TMs were what we're changing there. So what this changes to, just as before, is dt, capital T, little t, rate of change of temperature per time is some K, that may not always be K, but T minus Tm. Okay. Now, if the T, now this is the temperature at any time T, okay? If that T is greater than Tm, then that K is, is negative, because it is going to be cooling, okay? If the T is less than the Tm, the ice cube, then that K would be positive. So you see your initial conditions, well, I mean, your problem depends on what the physical state is, okay? No, they don't say that. They say in either case, cooling or warming, if Tm is a constant, stands to reason that K is less than 0. Oh yeah, I think that's true because the rate at which it's changing, that's just a rate. If T was less than Tm, then that's already negative. So the rate would be depending on the difference. So K would be always negative in that case. Now I think I've already mentioned this one, but not quite. See, I don't want to. Okay. I mentioned it, but we didn't go into the detail. Spread of a disease, a contagious disease such as the flu virus or something like that, cytomegalovirus as well, is spread through a community by people coming in contact with other people. So if X of T, let's do this on a clean page, okay? So if X of T denotes the people who have contracted the disease, I'm going to put number of infections. Okay. And Y of T denotes the number of people who have not been yet exposed. Y of T number not yet exposed. Okay. It seems reasonable to assume that the rate at which the disease spread, in other words, the rate at which the number of exposed people is increasing, okay, that's dx dt, that would have to be proportional to the interactions. So that would be x times y. That's one way to express it. Then your constant proportionality would be dx dt is equal to k times x times y. Okay. K is your usual constant of proportionality. Okay, now, if you had a very small fixed community with some fixed population, then the x and y are related to each other. If that fixed population is, say, p, then x is equal to p minus y, right? Or y is equal to p minus x. Because it's got a fixed population. And if only one person is exposed, then the others are not exposed, okay? But if you have 7 exposed, then the total population minus 7 is the number that are not exposed. So if you have a closed, small community, fixed population, then you have the X, and let's say fixed population of N people, okay, got it. Let's say nobody's exposed. So N is the number in the, N is your population, number in the community, okay? And none of them are exposed. You introduce one infected person, so now your X of T becomes 1, and if none of them are exposed to begin with, that's your Y of T. So then X of T plus Y of T is always going to be N plus 1, because you introduce that one infected person. Okay? I should have said 1 plus N. Doesn't matter. Okay? And then you go from there. But now you can say dx dt, because Y of T is equal to X of T minus N minus 1. So this would be K X of T, X of T, I say T and write an X, don't know what's wrong with this, okay, times X of T minus N minus 1, okay. No. I said it backwards. Okay, sorry. So that's not making any sense. I subtracted the wrong side. Okay. If that's true, then you subtract X of T from both sides. This N plus 1 minus X. And this will be N plus 1 minus X of T. Okay. And they left off the T's in there. So that's going to yield some type of result. And by the way, I don't know if you'll ever run into this, this leads to a situation we call a logistic regression. So that's what you use to solve it. If your population that's infected is very low, you're going to have a low rate of population, low rate of spread. But once the population that's infected increases, it goes up pretty rapidly, but then it tapers off because at some point your whole population is infected. So now it has to level out because there's no more people to infect. And that kind of an S curve there is called a logistic regression curve. And there are certain circumstances, especially if you have a fixed situation like disease or something like that in a fixed population, that's going to be the case. But it could also be the case, say, trying to think of an engineering type problem that would be vibrations and something, you know, if you have constraints on it and only so many things can shake, then, you know, that doesn't really make sense. But you could think of other circumstances besides diseases that could be the case. All right. Now, here's something. I'm guessing most of you have taken chemistry before, have you? Yeah, most engineering schools require chemistry at fairly low levels. So, chemical reactions, I know you did those. And let's draw one, for instance. And they actually call this a first order reaction. The disintegration of they're back to radioactive stuff again. Governed by the law differential equation that we use for that, said to be a first order reaction if it changes by the first rate. In chemistry, a few reactions follow the same empirical law. If the molecules of a substance A decompose into smaller molecules, it's natural assumption is the rate at which the decomposition takes place is proportional to how much you have there that is not undergone conversion. So dx dt would be kx again, just like we did before, where it's a negative constant. So let's say we have this chemical reaction. CH3, feels like organic chem, doesn't it? Okay, CH33 CCl. Okay. By the way, that is pretty sure they just said it and I can't see the word now. This is called T-butyl chloride. Okay. It's going to react with sodium hydroxide. Okay. And it's going to result with CH3. That didn't change. But now it's a COH. So basically the OH here replaced the chlorine, which would then result with good old table salt, okay, at the end, okay? I wouldn't want to use that table salt as table salt because I'm not sure. And what is the CH3OH? That's T-butyl alcohol. The OH at the end makes that an alcohol, okay? So, it sort of follows here that the rate at which this happens depends on how much of this you had to begin with. If you have a lot of it, it's going to go pretty quickly. If you have a small amount of this, it's not going to go as fast. Okay? Only the concentration of the T-butyl chloride controls the rate of reaction. You have plenty of sodium hydroxide out there. You just have a fixed amount of T-butyl alcohol. T-butyl chloride. Okay. Sorry about that. But in the reaction, only requires one part of sodium hydroxide. Okay, it's consumed for every blah, blah, blah. It's a pretty poor example, it seems like to me. I'm sure it's a fine example. So they say all that and then put us in generic case. If X is the amount of chemical C formed at a time, and alpha and beta are in turn amounts of two chemicals A and B, gag. Well, without any further ado, they just do this. dx, where X is the amount of a chemical substance, like that T-butyl chloride or whatever. dx dt, the rate at which that is changing, okay, and in this case would be decreasing because it's changing to something else. So that would be a K, which is a negative K, and that would be alpha minus X times beta minus X. Okay, now what are the alphas and betas? The alpha is the amount of, alpha and beta are the amount of the two chemicals initial amounts that you had otherwise in the problem. So in this problem here, that would be sodium hydroxide. Well, when sodium hydroxide is decreasing, this is if alpha is this X and those X's are the same. So the amount of this is changing with the difference in the amount here. So in other words, if the difference between sodium hydroxide and this is pretty small, it's going to be a very slow rate of reaction. Okay? Pretty large rate of reaction because the K is negative. If it's small, then so they don't specify what that is. I think that might be the NaCl, but Seems like that would be a plus. But anyway, this is what they use in chemistry a lot. Two things you have in great quantity, one thing you have in limited quantity, and that's the thing you're interested in. The rate at which it's decomposing depends on both of the other two. So I think here what they actually did was oh, I'm sorry. That's what it was. I didn't read far enough. This is the second reaction. I'm sorry. The first one was pretty simple. It was just like before. This is this one. CH3, I'm sorry. CH3Cl. Okay. Plus NaOH is going to CH3OH plus NaCl again. Okay. So this is methyl chloride and sodium hydroxide, and you form again methyl alcohol and, well, not again, this is methyl alcohol this time, and sodium chloride. In this case, the rate at which the reaction proceeds is proportional to the product of the remaining concentration of methyl chloride and sodium hydroxide. Okay, so that's what the alphas are. And the X is the chemical being formed, which would be the methyl alcohol. Okay, so that's what the amount of this being formed here is proportional to how much of this you have. So the dx, that's the X, and then this would be alpha minus X and beta minus X. If you're limited here, it's going to slow it down. If you're limited here, it's going to slow it down. If you have lots of both of those, then that's going to proceed pretty rapidly. That's what they're getting at there. Sorry, I didn't see they had introduced a different. That's called a second order reaction because you have two that you're having to deal with. Okay. Ooh, shucks. Ran out of time. I probably spent too much time on that last part. We'll move hopefully fairly quickly through the last couple of these. Mixtures and there are more than a couple, but still they're going to go pretty quickly. These are just examples you may run into. Differential equations. Okay, your test has nothing to do with those, I don't think. So do you want your test now? It's not actually going to be due till a week from the time we finish chapter 1, so it just gives you an extra day or two to do on it. We'll probably finish next time. I think I got them run off yesterday. I meant to. Yeah, here they are. Yeah. Everything that's on the test we've already covered, so this stuff is not. And will any of you see Jasmine? She was the only one missing today. Any of you know Jasmine? She's sat up there. Right. Good deal. Sorry, this last part is sort of blah, blah, blah. And I've got to book it to the clinic because I got a doctor's appointment. So if you're looking for me, I'm not going to be back on campus until probably 12:30, 12:45, and then I'll be in class again. So pretty scarce. Good deal.